In this work, we studied personalized federated learning from a Bayesian modeling perspective. This is a graphic model that we consider. We assume a set of global variables that are subject to some uniform distribution. Given the global variables, local weight is assumed to have a conditional distribution in form of Gaussian. Local datasets are assumed to be independent from each other, and the network output is regarded as a data likelihood. Here, F denotes the cross-entropy loss in the context of classification. In PFL, we need to optimize the local weights. To this end, we aim to maximize this marginal likelihood, which marginalizes out the posterior of the local weights. This means the training process considers the statistical estimation of the local weights, such as uncertainty. We use EM to conduct clockwise coordinate descent. At each step, we fix the global variable and optimize the posterior estimation of the local weights. At M step, we do the reverse. In summary, we propose a principled method to perform PFL which considers uncertainty and model deviation. In typical federated learning setting, all the participants jointly train a global model to minimize the averaged loss function. In personalized federated learning, every client adapts the global model to its own dataset. The optimization objective depends on the local models instead of the global model.
Personalized federated learning is developed to address the issue of data heterogeneity. This common problem arises from data separation, as each client collects data that is correlated to its local environment. In the context of image classification, we denote the data distribution as a joint distribution of image and label. Label distribution skew can be defined as the same conditional distribution Px given y, but different Py across clients. There are other types of data heterogeneity. Red color marks the part that is assumed to be varying across clients.
Our method builds upon posterior of local weight. Therefore, it can generally address all types of heterogeneity. To optimize the Bayesian framework, we need to obtain the posterior distribution of local weights. Based on the graphic model, we observe the conditional independence across local weights. This can help factorize the joint probability of the local weights and simplify the further analysis. Here, we assume the conditional prior Pwj given W is in form of Gaussian. This enforces local weight to stay close to the global model, and empirically it works well. To estimate the posterior distribution, we introduce factorized variational approximation in this form. With all of this equipped, we optimize the Bayesian framework by maximizing the elbow of the marginal likelihood using EM, such that we have the following objectives at the E step and the M step respectively. It is able to derive a closed-form solution for the M step, define confidence value that considers the model deviation and uncertainty. We note that the optimal global weight is obtained by averaging the mean estimation of the local weights. weighted according to the confidence values. Furthermore, the confidence value influences local weight training through the KL divergence at the E step. In summary, we obtain a more principled method of aggregation and personalization. They are influenced by the confidence value, which considers model deviation and uncertainty. We conduct extensive experiments with many baselines and various datasets. This table shows performance under label concept drift, which is a type of data heterogeneity. Here, PM stands for the personalized models, and GM stands for the global model. We evaluate the global model with a complete dataset and evaluate the personalized model with the types of data a client has. As we can see, our method greatly outperforms the baselines and especially on more complicated CIFAR 100 dataset. This table shows a distinct strength of the Bayesian framework. When data is scarce, our method significantly outperforms the baselines. Thank you for watching. For more details, results, and the code, please visit our project page.